this is going to be pretty much a chemistry talk followed by mathematical ways of trying to solve our problems. And the way I would like to begin the talk is by explaining what our main problem in design is. So let's imagine that we have the diamond, the structure, and the way we usually go around it from quantum mechanical calculations is that we calculate our wave function, and from there we calculate the properties. And sometimes we go and try to understand the chemistry behind these properties, analyzing the chemical bond. So we would say naturally that a diamond has a big band gap because it is a covalent solid. Now, the problem is that if we now have the question of how about silicium or germanium, which actually have the same structure, we would have to repeat the calculation all over again. And actually, the result would be different. One would be a semiconductor, for example. So if the property we're looking for, like in our case here today, superconductivity is very expensive, then that means a huge data mining. So the way we try to go around it is to actually inverse the way we interpret this problem. First, we do the chemical bond analysis, and then from there we try to understand to calculate the properties. But actually, that means that we need to have models that will link quantitatively our system with the chemical bond, and for that we will use topological analysis. And we will need to have a quantitative link between this bond and the property. So we will need correlators or simple models from this bond to the material property. If we actually really want to go to high throughput, we actually also need to make this part here pretty fast, which is not necessarily the case. And for that, we can use machine learning, as I will show it by the end of the talk. This actually means we will avoid the wave function calculation. So that will actually give rise to the scheme of my talk. So I will devote an introduction to what we call topological analysis of the chemical bond, giving you two examples, the electron density and the electron localization function. Now we will use that to deriving properties, such as understanding why metals can become insulators under pressure, or how to calculate superconductivity in a cheap way. And from here, we will see that we still have many problems to make it high throughput. So in order to go large scale, as we aim in these seminars, then we will need to introduce some automatization and machine learning that I will speak of at the end. So all this part is ongoing. So I will show you what problems we're still facing. So starting from the chemistry introduction, which will be a long introduction. So we actually want to mathematically characterize the chemical bond. So starting from our wave function calculation, we will have a 3n if we just take coordinates into account body. What we want to do is we actually, if the way chemists think about systems, atoms, and bonds is in 3D. So we want to go back to reduce this dimensionality of 3n to 3D again. So we will use a chemical function calculated from this wave function, such as the electron density, it's a typical one, and we will analyze the shape of this function through Morse-Smalley, like in a Morse-Smalley complex. Let's see one example. If we go for the electron density, we can derive it directly from the square of the module of our wave function. It has also some other advantages. It is experimentally accessible. So everything I will be saying today, it can also be calculated from X-ray diffraction. And from the theoretical point of view, the electron density is well defined within the exact many-body theory, and it is supported by the Hohenberg and Kohn theory. So let's see what we do when we do what it's called quantum topology, chemical quantum topology. So we will take the shape of the density. Let me So this is the image I like the most. So here you have benzene. In benzene, we have this ring of 6 carbon atoms with hydrogens linked to it. And when we look at the electron density over here on the plane, we instantaneously see that the electron density is reflecting this atomic composition of our system. What we will do is not only we will look at these cusps, which we associate to maxima in our topological analysis, we will also look at saddle points. So these first order saddle points, which are reflected here by the red spheres, will be assimilated to chemical bonds. In this way, we can tell that carbons are linked together, carbons and hydrogens are linked together, but for example, there is no link between neighboring hydrogens. So this is a way that people coming from quantum chemistry used to know when there is a bond or not, when we don't know the system. So at the end, we can draw our benzene structure. This is extremely useful, especially in weird systems where we have no intuition. I also tell my students coming from physics that it also helps you being a chemist if you don't know chemistry. And it also helps us when we, for example, analyze structures under high pressure that I'll show you later, when we have no idea of what is going on. Now, I have shown you this benzene system from the electron density. But the electron density, if you realize what I'm showing you here, it will have maxima only, not only, but most commonly only in the nuclei. And chemistry comes in many occasions not from where are the atoms, but from where are the electron pairs. We will not want to know where the lone pairs, like in water, where you can imagine the two lone pairs. We will want to know bond charges to know whether a bond is single or double. So for that, we actually need to go back to the initial structure I gave you for what we call topological analysis. And we will need another chemical function that will reveal that will have maxima associated to these structures that I'm telling you about. And this is the electron localization function. It can be interpreted as an excess of local kinetic energy density due to polar repulsion. What does this mean, actually? If we want to picture it this way, electrons in a lone pair are paired, so they're happier than if they're, for example, in between the two lone pairs, because they will see electrons of the same spin. So in these regions, they will be faster. So kinetic energy density, so kinetic energy, so the speed defined locally, will tell us whether electrons are happy or unhappy in a given region. And that's a way to actually picturing this chemistry I'm telling you about. Now, electrons, we want to only take into account Pauli repulsion, which is what is supposed to be giving us this structure into bonds and lone pairs. So this is the total kinetic energy density, and we will take out this quantity. This quantity is called the bosonic kinetic energy density. And let me show you pretty fast. So if we put all electrons not in a fermionic system, but all at the same level, so in the first orbital, then the density will be just related to this orbital. So we can actually define the gradient of this orbital related to the gradient of the electron density. And from there, it is pretty straightforward to define the kinetic energy density in this system as the one that I just showed you. So in this case, the kinetic energy is just related to the fact that we have these particles not to their fermionic density. So the difference in between the two is called the fermionic energy, kinetic energy density. Now, these kinetic energy densities, obviously electrons will be faster if the electron density is higher. Kinetic energy densities depend on the electron density, and this would not allow us to see what is happening in the valence because the core has a much higher electron density. So what we do is we divide by the first term in the expansion of the kinetic energy density, which is the homogeneous electron gas. And from there, we just map it so that the electron localization function, as it is called, will run from 0 to 1. So let me show you one example. This is the nitrogen molecule. And here we have one nitrogen atom, and here we have another nitrogen. Now, this polykinetic energy density, as I was telling you, will only peak at the cores because they have a much higher electron density. Once we divide by the homogeneous electron gas, we obtain the red curve, which I find just amazing every time I show it, because just by doing that, you retrieve the full chemistry of this molecule. So you have here that electrons are slower in the cores, where they're extremely localized. They're slower here in the bond region, and they're slower in the lone pair region. So basically, you have your full Lewis structure just from this curve. Now, the rest is just a Lorentzian mapping. So here we have the red curve, which will be our new function, which will have a maximum every time we have a Lewis pair. And if we plot it in 3D, we obtain something like this. So we have here the nitrogen molecule, and we have the nitrogen-nitrogen bond and the nitrogen lone pair. So up to here, we have this function. Now we need numbers, so that, remember at the beginning, I was telling you we need numbers to be able to identify, to characterize these bonds, give them numbers, and from there derive a model where we can predict properties. So what we have done in the past is implementing this into a code that can find all these critical points, can make the integrals over these regions, and doing the plotting. Here you have an example. So this is for diamond. Here we have diamond is form of carbon atoms joined in a fourfold manner. So here we have one carbon atom, the carbon-carbon bond, and another carbon atom. That's what you get from the electron localization function, and that's the list of critical points that you get from the code. You can also integrate these regions, and then what you obtain is, for example, that the bond over here has 1.97 electrons, pretty close to the 2 electrons one would be expecting in diamond. Same for the core. So the core of the carbon has nearly 2 electrons, also very close to expected. Now, if you compare, for example, this is the volume. The volume of the carbon atom is very small. This is all in atomic units related to the bond, which is also very chemically, we would expect it, because the core is known to be very small, and it's actually very static with respect to transformations. It's the valence, which has a bigger volume, so it can be breathed easily, the one that will take up everything when this compound will react. Now, from this function, we can also identify not only localized bonds, like in diamond. I have here the example of a metal. This is aluminum, and here you have the core of aluminum, the 2 shells, and then here is the valence. Now, if we actually introduce the homogeneous electron gas here, we will easily see that the ELF that corresponds to a metal is 0.5. And that's exactly here. So in a metal, we expect this valence that actually does this wavy thingy in the valence region. Since this is a very, so if you remember this profile with respect to the metal, you can see that this topology is not persistent with respect to that one. So the way to actually, if we visualize it, we see it like a continuous surface at all these values. And basically, going back to the localization of critical points, we are able to make these bifurcation trees and actually measure this distance over here with respect to this distance, and this will allow us to characterize, for example, a covalent bond with respect to a metallic one. And this is actually extremely useful. For example, let me show you one example of something that happened, I think it was like 10 years ago. maybe more now, because it was in my thesis. Yes, certainly more. So here you have this new experiment of sodium and potassium under pressure. So if you ask students in first year chemistry, what is the characteristic of sodium or potassium, they will tell you it's a metal. So it's a conductor. Now you take any of these compounds, you put them under pressure, and for that you actually take a tiny sample of this metal, you put it into 2 diamonds, and you compress enormously up to 200 gigapascals, which is huge. But at that pressure, actually, you make the measurement, and it has become insulated. And that was completely astonishing, among other things, because if you think about orbitals and squishing, you would think that everything becomes more metallic because there are more overlaps. So what was happening here was all the other way around. When you already had a metal, it became an insulator. So it was, at that time, it was extremely interesting and important to understand what was this new state of matter. And it's extremely simple if we use the function I just showed you. And just actually the pictures I showed you from aluminum. Here you have sodium when it is a metal. So here you have the cations and the homogeneous electron gas, which is a flat profile in between them. So those are the delocalized electrons. You start putting pressure to it, and instead of delocalizing more, it localizes. So you see these features appearing here. And actually, when it goes to insulating, that's the picture you get. So you have your cations, and the electrons have become completely localized in the voids. So basically, at that stage, from the physical point of view, in order to minimize the Gibbs energy, your electrons will form pairs that will become like an anion, but there is no core inside. So they will form what are called pseudoanions. We have then cations and pseudoanions. So basically, this structure is a pseudo-ionic structure, and ionic structures are insulating. So we can understand this new state of matter as a pseudo-ionic structure. We can look at what is happening in the electron localization function further. Let's see, for example, here in potassium, here you have the cations, and here this is an isosurface of ELF equals 0.3, and here are the valence electrons completely localized in the voids. Here, if you look at 0.9, you basically can just picture these localized electrons. And if you integrate them, you have like 1.7 electrons. So it's pretty close to an electron pair, localized there in the void and giving rise to this new state, insulating state. As a matter of fact, because this will come back later, if you take compounds with potassium and real anions, the anions will get into the same position in the crystalline structure. So basically, that's what's called the effect, the equivalency in between chemical and external pressure, meaning you can have a compound stabilized by pressure, or the same compound stabilized by introducing another atom that will compress the atoms around it and will have the same effect as hydrostatic pressure. And why is this important? Well, now we're going to superconductivity, and basically we were interested in, with some colleagues of us, in superconductivity, obviously, because it has two key features. It has null resistivity and perfect repulsion of magnetic fields, and this leads to important applications in electronics, levitation. Basically, it would be great if we had them. However, superconductivity of type 1, which is the one we're interested here, basically happens as we have a normal state at normal, typically high temperatures and magnetic fields. And as we go lower in the pressure, we lower the pressure, we can enter into the superconducting state. What's the problem here? The problem here is that actually this TC, or critical temperature, is very low. for normal compounds. So in aluminum or in zinc, it's around 1 Kelvin. So everything that you would gain from the fact that you have null resistivity, you would pay even more to actually have this temperature. So superconductors would be extremely relevant to energetics if we were able to design new superconductors at temperature, at room temperature or close to room temperature, so that they would have critical temperatures at room temperature. Problem here, it is extremely expensive to make these calculations to predict the critical temperature. So the large scale data mining is out of question. Moreover, these calculations are really at the verge of what can be done. It needs electron phonon coupling. And for example, we had this aluminum hydride that was predicted to have a TC of 100 Kelvin, and then experimentally synthesized later on, and it only had 4. So it is really a hard quest. And what we thought with our colleagues working in superconductivity is that we really needed to understand what was going on in the chemical bond of these compounds to actually propose some kind of model that would allow us to make affordable TC predictions. So we decided to start from hydrogen-based systems, and that's because in the last years, new compounds have been proposed based on hydrogen that have pretty high TCs, around 200, 260, all based in hydrogen. The problem here, and it goes back to what I just showed you, is that they are high temperature, but also high pressure. So it's still not useful from a technological viewpoint. Now, as I was telling you, we can hope to substitute hydrostatic pressure by chemical pressure. So that's a second step that is feasible. Synthetic chemists know how to do that, but the first thing we need is to actually be able to predict new high TC superconductors, even if they're high pressure. So let's start. We did the electron localization function on nearly 180 systems and classified them. Here you have the results for the electron localization function. Now that I showed you how to interpret it, I think it's pretty straightforward. So here you have hydrogen molecules. Here you have, for example, like in the case of the high pressure system I showed you, so we have electrons in a void. Here we have hydrogen atoms that are separated, so they are stretched. So we classified them all, and we tried to understand, which is the first thing one should do in this kind of trying to predict in this inverse design. So we classified our systems in terms of TC and the periodic table. As you can see, the high TCs are all concentrated for S and P atoms. So since I have it in my background, so you can just check it's both ends of the periodic table. And it's these systems in pink, violet, and green. So those were actually the non-charged ones, covalent, molecular, and weak interaction. They are all hydrogen-rich systems. If we plot the TC with respect to the hydrogen fraction, we see that they all need to have a high hydrogen composition. And if we actually plot them by families, these lines are just to guide you, but you can see that we need to go to, in every family, to have the high end of the hydrogen-hydrogen bond. Now, the problem here that I'm showing you here is that these are some of the trends, but actually we have lots of outliers over here. So that's the point where our colleagues in superconductivity contacted us, because they had necessary but not sufficient conditions. So basically they needed better correlations to actually be able to design new superconductors. So we went back to this chemical bond analysis and trying to understand, as I showed you, what is the localization-delocalization pattern. So what we did was to construct a a wave function in real space, because remember, all these analyses are in real space, of a Cooper pair. So we all these and all the definitions of the superconductors of this type of superconductors start from the BCM model, which is based on a Cooper pair of electrons, but this is in reciprocal space. So we had to redefine it in real space, and from there we could construct our models. These are the L functions in a metallic model that we started from. And as you can see, as we compress, here we have hydrogens more separated than here. Our L value here increases, like in metals, like what we just saw before. Now, if we go to the Cooper pair, you can see that it also increases with pressure. So that gave us hope with this very simple model to actually go and check what was happening in all these systems from the calculations. So what we did is, let's start from this yttrium example. So we have this yttrium cell, and this is the electron localization function at a very high value, 0.9. We start diminishing, and some connections appear that I'm plotting on the right here and there. That actually means that we have a new saddle point appearing in our field. So that means we have a saddle point at this value, and then this allows the appearance of this new connection. We keep decreasing, and this allows us to retrieve the different, so from top to bottom, the values of the saddle points and these connections, until we actually have a network that is all connected. And that's what we were looking for, because that would mean a complete delocalization of the electrons. So that's what we called the networking value. We did it for the nearly 180 crystalline structures, which, as you saw, come from very different bonding types, but have the same localization, delocalization features. And we plotted them. The results are not great, but actually, once we mix them with what we already knew, with the hydrogen composition, we got to this correlation, which was much, way better than what was up to now. And actually, it didn't need expensive calculations. It's just a DFT calculation. So we were at this stage that actually everything that I showed you here, this finding the critical point that leads to the delocalized network value, was done by a student in the Basque Country who was extremely patient, because he did it by hand. So looking at all these isosurfaces. So that's where we start on this automatization. So basically, the summary of this chemistry and physics part is that the networking value is able to capture effectively how sensitive the electronic cloud is to lattice vibrations, so how we can reflect the TC. It improves all other structural and electronic indexes that had been previously proposed. It's cheap because it only requires DFT and ELF calculations. So it would open the way to screening new superconductors and inverse engineering if, number one, this was automatic. So that's where it all starts, working with my student Trinidad and Yvonne. So the starting point, we had our code that I showed you before that allows us to retrieve the electron localization maxima and the saddle points. So basically, we go from this typical picture of the isosurface to a graph of all the maxima connected through the saddle points. Now, how to define these delocalization networks? We needed to define, so basically, it is delocalization in 3D. So we need the condition of periodicity in 1D, which is basically that one node is connected to its translated to the one in a periodic unit that we don't know in which direction, and this needs to happen in 3 directions. So starting with the periodicity in 1D, let me show you one example here. So we have our nodes, and 3 is connected to 2, to 0, and then it takes it to 3. And it happens, and this will be our main direction. Now, this actually meant at the beginning of this coding that we didn't know how many units we needed to take into account. So basically, in order to reduce that, we decided to use periodicity and to reduce everything to the repeated unit. So for that, we started from here. Let's say we have our node 0 connected to 3 within the same unit and to 1 within the same unit. And we keep the fact that it's within the same unit cell as an attribute. So here we have 0, 0, 0. Now we look in the cell surrounding, let's say this one up here, and our 0 is connected to 2 and to 1. So this is accumulated information with the translation. And finally, with the 1 next to it in -1, 0, 0. And actually, that's the first part of the algorithm. Now we need to check, since we need to check that it is connected to a translated cell, and now the translated cell is within the cell, we need to look for loops within this cell. And for that, since we have the attributes, we just need to check by summation of these vectors that we have indeed translated to another cell. In this case, for example, going from 3 to 2 to 0 to 3, from 3 to 0, from 3 to 2, from 3 to 2 to 0 to 3, we have a net translation of 1 minus 1, 0. And we need to do it for all possible loops, since we need to check what is everything that is happening. So for that, we needed to construct these graphs of, we actually did adjacency matrices, and we basically checked which atoms were repeated. Like for example, here, we were focusing on 3, which is repeated here, which is the cycle we were checking before. And then we just need to evaluate the attributes through the branches. And we repeat that for 3D. Now we have the automated algorithm, which actually was very good because it worked good enough, but we still had big errors with respect to what we had obtained visually, which is something when we were encoding it, I found it pretty interesting because to the naked eye, the fact that they were connected or disconnected and in 3D was completely obvious, and it turned out to be a nightmare to compute. Now, one of the errors we found was this kind of nodes where actually you see they're all symmetric with respect to a central node. And actually, what was happening when we checked what these nodes were is exactly that. So remember, I told you that you saw for example, in the aluminum that we had the electron pairs in the shells. So that's exactly what was happening here. We had all these maxima around the atoms, and these profiles are very steep, and we're working with grid data. So we need to use thresholds in order to determine whether 2 critical points are the same or not. So basically, we had that these critical points, we were not able to find that they were actually linked together. Since we're aiming, we could obviously go for improving the algorithm, but since what we want is something pretty fast and the core in chemistry remains untouched, let me show you one example. This is argon. If you put pressure to it, only the valence shell will be affected. This part stays exactly the same. So we can just use atomic information on this part, and we will know where all these maxima around here are located. So basically, what we did is to keep this information, this radii, internally in our code, and add all these maxima that were appearing around it as one unique unit. So all these connected by default. Results improved, but we still have a long way to go. And that's where we basically are now. So analyzing which systems are giving errors. Anyhow, with these results, we're already able to start working on the prediction of new high TC superconductors, and that's what we will hopefully do in the coming months. So I've just shown you how we have coupled our critical point determination with the networking value determination in our new code of TC stream, the automatic determination of critical temperature. Now, last part I want to show you pretty fast is how to go faster, because everything I've shown you are high symmetry phases. But if we go to low symmetry phases, like the one we have here in hydrogen, this is a metallization of fluid hydrogen. Here we have 100 of atoms. And let me tell you that these calculations, the dynamics took 13 days. And since once we have this calculation determining the electron localization function, took us twice as much, which is not acceptable, obviously, for determining the networking value. Nevertheless, one could think, if this the electron localization function would be calculated without having the wave function, we would be done. So then we started collaborating. That's a project, and not actually a previous project that hopefully will merge with this one, with some colleagues from Catalonia, where they wanted to use this data to predict the electron localization function. So basically, since every grid has lots of lots of data points, then they used this data to feed a neural network, and just using the geometry of nearest neighbors and 1% of the ELF data points, trying to predict the electron localization. Visually, it looks great. Now, the only problem is that once you go to an histogram to actually see where the errors in the prediction are coming from, here you have the real ELF value, and here you have the predicted. This is logarithmic, so anyhow, it's pretty good. But as you can see, the biggest part of errors are coming from exactly where we are looking at, which is the delocalization region, ELF 0.5. So we need to improve it. I really believe we can do it by the use of these promolecular densities, so atomic densities that have already been used today. That's something to check. Good news is that the computation of the electron localization function went from 25 days to 3 minutes, including the training. So that's the end of my talk. I hope it was it gave you an idea of what we're trying to do in analyzing the chemical bond and coupling it to predict properties. So through both the electron density topology, the electron localization function topology, how to connect it to superconductivity, defining 3D delocalization networks, how it correlates with the TC, and hopefully allow a high throughput analysis of potential new high TC systems, how it can be automatized by neural networks, hopefully better, how it can be, how the networking value can be automatized by this treatment of periodic systems. And here's some pictures. Yvonne, I took yours from the web. Sorry about that. Hope you like it. And this is the student who did all the superconductivity analysis here in Paris in collaboration with the people in the Basque Country. And this is the people in machine learning and in the fluid hydrogen I showed you at the end. And thank you for your attention, and I will be glad to take your questions.